if you have equilibrium or maybe associations between intermolecular association, in some case it can be tricky. But even I don't know, I don't have the exact molar mass of the compounds, but usually we in the lab with the 500 megahertz spectrometers, we still are in this area.
And a quick second question: if I want to do a nosy, do I have to see with you or?
No, it's routine experiments. It's on the sample changer. Yeah.
So there's only the one nosy experiment I can choose?
Yeah, available, there's only one. Okay. NOI effect is not a big effect, so it's not very sensitive, so it's longer than a COSY or TOXI experiment.
So it's overnight, typically?
Oh, no. If you have a 10 milligram compound, usually you will get the nosy in 1 hour.
Okay.
But COSY in about 5 minutes.
Yeah. One question for that with the I notice when I charge my molecule, like my tubes, let's say for carbon, which I want to do during the day, I charge it sometimes with 100 milligrams. So the carbon is fine, but the proton sometimes looks really messy,
because it's too concentrated.
So then typically I do sometimes 2 tubes, so one only for proton, where I have 5 to 10 mg, and one for the carbon. So there is no solution to that problem, I guess.
Do you really need the carbon spectrum during the day?
Sometimes, yes. Yeah.
So if you need it, you have to make very concentrated tubes, and so usually the proton spectrum is not so good. For molecules like this one, or maybe 2 or 3 times bigger, but so it's quite 10 milligrams would be okay during the night for all experiments with the standard conditions, with the standard number of scans, and usually can get a complete analysis within 2 hours with only 10 milligrams.
Okay, that's good to know. Thank you.
Sorry. Another spectrum, proton 2D spectrum, which can be very useful, is the J-resolved proton spectrum. This is a quite fast experiment because you only need about 10 minutes, so it's quick. And this experiment aims to simplify the multiplicity, proton multiplicity, and so you will get in the horizontal dimension you will get the pure chemical shifts, and in the vertical dimension you will have the multiplet pattern. For example, here you can see this is simple because you can see it already on the one-dimensional spectrum. You have a triplet, so you can see it here, and you can measure the coupling constants. Here you have a singlet, quadruplet here, but in this area it was not so straightforward in 1D spectrum. And with the J-resolved, you can see that you have 2 big doublets, one here and one here, with the same coupling constants, and another system with 2 small doublets here. Okay, so the J-resolved can be very useful for when you have overlapping multiplets, and it's very quick. It's in the list of routine experiments, so don't hesitate to use it. It can be very informative. Next, we will go to the heteronuclear proton-carbon correlations. So the main 2 are HSQC and HMBC. They differ by the number of bonds for the correlations. So for HSQC, we are looking for 1 bond, J1 CH couplings. And for HMBC, it means heteronuclear multiple bond correlation. So here we will see 2J or 3J carbon-proton correlations. HMQC gives for proton-carbon spectra the same information that HSQC. It was sort of the older version. It's not really the same pulse program, but we have the same information. For recent spectrometers, HMQC is usually of lower quality, but for very old-fashioned spectrometer, it's more robust. But here, we don't need to use it anymore. Only use the HSQC experiments, and we have a variant. I will show you later that we have an edited HSQC that is much more informative. So HMQC is still used. I use it only for other nucleus and carbon-13 when the coupling constant is not precisely known. Okay, so in routine, the most used proton-carbon correlation is the edited HSQC. So all these experiments are detected with the proton signals. So it means we call them inverse correlation. And since they are detected with the proton, they are very sensitive. So you don't need to increase the number of scans of these experiments when your proton spectrum is okay. This is really important to save spectrometer time. I often see samples submitted with very, very long 2D experiments, and usually it's not useful. So the standard time for an edited HSQC is now 4 to 5 minutes, because we have improved them with a quicker, not on all the spectrometers, but on those who could do it, we have sped up the experiment with the non-uniform sampling detection scheme. Anyway, the standard duration was 15 minutes, and we have sped it up to 5 minutes. So this is a very quick experiment. It's very, very much quicker than performing a DEPT or a J-mode direct carbon detection. So you can stop using DEPT or J-mode and use only edited HSQC. So direct carbon one-dimensional spectrum, because it's not mandatory, but it's almost. So you will make, when you have a compound and you need the characterization, you will get the proton spectrum, direct carbon, and instead of J-mode or DEPT, I encourage you to use only the edited HSQC, which is much, much quicker, and it will give you much more information, because you will get the depth information with the sign of the correlation peak, positive or negative. This is the same than depth information. And you will get the correlation between proton signal and carbon signal, and you will know which proton is on which, related on to which carbon.
A quick question, Elsa.
Yes.
So positive or negative, so which corresponds to carbon and CH2 and which to CH and CH3?
So since we observe J1, 1J proton carbon couplings, we don't have quaternary carbons here.
Okay, yeah, sure.
Okay, and it's like the depth. conventional will be to have the CH2 negative, so blue here,
Okay.
and CH and CH3 positive. But in some cases, when the most abundant site is a CH2, maybe it can be misphased. You just have to invert it.
Okay, so
Okay.
you should check with a proton to identify one proton, and then you can see which.
Yes, usually if you have maybe some aromatics or some methyl, you will know which one
Who is who? Okay.
should be up.
Thank
It's
you.
the same than in depth, in fact. If you see that the phase is inverted, you just have to shift it 180 degrees, and it's okay.
Okay.
Just here to show you, here this is just a zoom. Here we had in the J mode, we had a node signal because we have two very close carbon peaks, and one is a CH and one is a CH2. They are very close one to the other. And here with the edited HSQC, we can see very well which one is which. Okay, so next, HMBC. HMBC is the experiment that could allow you to detect quaternary carbons without direct 13 carbon spectrum. In some cases, when we have very few compounds, if you have already tried the cryoprobe in Villejean, for example, in some cases, quaternary carbons are still very difficult to see, and HMBC can make them available via carbon-proton couplings. So as we are looking for long-range couplings, the usual coupling constants will be smaller than 1J. So usually they are in the 5 to 20 Hertz range. So we need to use longer delays in the pulse sequence, and this induces signal losses due to relaxation. So the HMBC experiment is intrinsically less sensitive than HSQC. But in the standard parameter sets on the sample changers, we already have taken this into account. So the standard datasets are okay, both HSQC and HMBC for a standard tube, let's say about 10 milligrams of compound. In an HMBC, we have something in the pulse program that should suppress intense 1J coupling, but in some case, on very intense peak, we still see them. So here you could get on some intense singlets, you could see residual 1J coupling like this. For assignments or interpretations, remind that HMBC, so we are looking for long-range coupling, but the correlation intensity is not related with the distance. Here, for example, on this line, we have the couplings of carbon 3 with H2, H9, H10, and H10, and the more intense is here for the 10. So it's not related with the distance. And so this is the aliphatic part of the molecule. And one thing you can remind is that for aromatic systems, 3J are always more intense than 2J. Usually in aromatic systems, we almost don't see the 2J couplings. So in some cases, you can see here that we observe a lot of correlations. So it can be, in some cases, it can be a bit tricky to assign, but if you need the long-range information, HMBC will be the experiment you need. Okay, now I switch to other nuclei. So the most often observed are fluorine, phosphorus, or boron. So when you want to observe a nuclei, you have to be aware of the number of spins to know if you will have a proton-like spectrum or not, proton-like coupling. The frequency will be very important to know if we can observe this nucleus with standard probe heads or not. The natural abundance, receptivity, these two factors will be very important for the sensitivity of the NMR experiments, and the usual chemical shift range to know if in which window you have to look for the signal you want to see. Usually, you will get when looking at an heteronucleus, you will get reliable chemical shifts because the spectrometers are on recent spectrometers we won't have shifts, so chemical shift will be reliable. But if you want to be very precise in the chemical shifts, in some cases you will have to use a reference compound in a coaxial cell if you want to be very accurate on the chemical shifts. Okay, so just very quickly for fluorine, fluorine is very easy to observe because it has a 1/2 spin number. So like proton, it's very easy. It's 100% abundant. It's very, you have always very intense signal because it's very sensitive. And chemical shifts are spread over a very large range. For phosphorus, it's quite easy too. It's more sensitive than carbon-13, for example. But for another nucleus like boron, it can be more tricky because we will have 3/2 spin, so it will induce unusual coupling patterns, for example, in proton spectra. And we have another isotope of boron, which is a 10 boron, which has a 3 spin, and one is 80% abundant, the other is 20% abundant. And moreover, for boron, if you are working with Pyrex sample tubes, you will get probe head or tube signal, so it can be a difficult nucleus to observe. With heteronuclei, we can get couplings. We can get sometimes strange things like isotope shifts. Here I show you a funny example of boranyl, which was made in Corin team. Here we have a funny pattern in the fluorine spectrum with two different signals, because here the rotation of these phenyl groups, phenyl group is hindered by the big group here. So the two fluorine are not equivalent. We have a first one here so both fluorine as coupled together with a 85 Hertz FF coupling constant. Here we have a coupling constant with the boron here of 26 Hertz. And here we will have two superimposed signals, 80% doublet with fluorine and quadruplet with boron for the fluorine with 11 boron, and 20% broad signal for the fluorine with 10 boron nucleus. So here we have two superimposed signals with a quite complicated